Hello all. We're continuing in our unit on metric conversions and significant digits, and we're going to be looking at rounding today. I know you don't think you need a review, but you probably do. We're going to do some significant digits in measurement. I'll also teach you how to count significant digits, and I'll give you a little, this is a shortcut. It's called the Atlantic-Pacific rule. Um, we'll have some classwork, but no need to worry about it now. I guess your homework is that you need to do Cornell notes based on this video. The goal today is to talk about precision, accuracy, and uncertainty. So, accuracy is actually how close the average measured value is in a group of measurements to the true value. So, we use these machines to measure something's mass, for instance. Let's say we have a scale to measure something's mass. One of the things that's tricky about that is that two different scales could give different measurements, and the object that you're measuring has only one true mass. So if you take a bunch of measurements from the same device or even different devices and you average them together, and that average number is close to the actual value, then we're going to call that an accurate reading because it has to do with the average being close to the actual. Precision is different. Precision is when you take some readings with a device and the readings are really similar to each other. They're not necessarily close to the actual value, but they're really reliable compared to each other. When I'm considering the difference between accuracy and precision, I usually think about, let's say, a bathroom scale. If I get on that bathroom scale 3 times in a row, and it gives me the exact same value every time, but those values are not my actual weight, then those values are precise because they're really close to each other, but they're not accurate because they don't average to my actual weight. So that's sort of my quick definition of how to do that. So when you look at these diagrams are bullseyes, and if you look at this bullseye, you see that the darts have all gone right into the middle of the bullseye. So that means that not only are they precise because they're really close together, but they're accurate because they're right there in the middle. And then for the next one, we have 3 values that are far apart from each other and they're not close to the middle, so that's neither accurate nor precise. In the next one, then we have 3 values that are really close together, so they're precise, but they're not very close to the middle. And then over here we have 3 values that are not very close together, so not precise, but they are accurate because they're right here around the middle. They average to the middle. Accuracy and precision are important in chemistry, but in all sciences, because accuracy and precision are things that we need to consider when we're using machines to measure data values, and we use lots and lots and lots of machines to measure data values in chemistry. Not only scales, but all kinds of machines to measure volumes, to measure densities, to measure lengths. We need machines for that stuff. So rounding, here's a quick review. When we are rounding a number like this one, for instance, let's say that the instruction is to round to that digit, the 8. If that's the instruction, then it's not really the 8 that's our primary concern. What we actually need to be looking at more carefully at the moment is the digit that follows the 8. In this case, it's a 7. And the rule is basically that if this number is the number 5, or if it's higher than the number 5, then we go back to this 8, and the 8 will jump up a digit. So since this is a 7, then I'm going to have to jump this 8 up a digit. So that's going to be read as 243.9. Now, we're going to be talking about certainty and uncertainty today, which is why I'm bringing this up right now. Certainty and uncertainty are basically concepts that reflect themselves in the number of digits that you see in a number. So the more digits that you see, the more certain we are about that, as long as we're following the rules that I'm going to talk to you about in a few slides. So those rules are based on this idea called significant digits. You can get a grasp of significant digits by looking at this thermometer to start. So one thing you can see is that the temperature right here looks like it's about 5 degrees Celsius. At least that's the 5. This temperature is actually higher than 5, and we're going to use some logic to figure out what it is. So if this is 5 and that's 10, then obviously this is going to be 6, 7, 8, 9, 10. Now, to me, I can see that this actual temperature is definitely above the 6, but also to me, it is below the 7. It's not quite at the 7. So what we need to figure out is what the temperature would be. So the correct reading of this thermometer will include all of the certain digits and one estimated digit. So the certain digits, for me, is the 6, because I can definitely tell it's above 6. And an estimated digit is going to be 0.5. Now I know that a lot of you don't really want it to be 0.5 because it looks so close to the 7, but if you can't really tell whether it's going to be 0.6 or 0.7 or 0.8 or 0.9 because you don't have any markings to help you, then usually we're just going to go with 0.5. So I think that the temperature that we should write, if we're going to use the rules discussed on this slide, is the certain digit, which is 6, and one estimated digit, which is going to be a 0.5, because I know it's above 6 and I know it's below 7, but I don't know much else other than that. Now, just as a quick review, this one's called a certain digit and that's called an estimated digit, and both of those together are called significant digits. So how many significant digits are in my answer? It's 2, because I have the 6, which is certain, and the 5, which is estimated. So when we count significant digits, there are a ton of rules to remember. Well, maybe not a ton. It's really only this many. But I'm going to teach you this way because this is the tried and true traditional method. But there is another way, which I'll go over on the next slide. So I tried to organize this in a really sensible way. We start with basically like some general rules that would apply to any number that you'd look at. But then there really are 2 different kinds of numbers that have one rule that differs between them. So any number is going to get, you're going to have to apply all of these rules. But if that number does not have a decimal, then also apply that rule. And if the number does have a decimal, then apply this rule as well. So let's start. Take a look at this number. Ignore that it has a decimal for now. We'll come back to that. But here's a general rule. A general rule is that when we're counting the number of digits in a number that are significant, you start counting from the left with the first non-zero digit. So I'm going to start counting from this side of the number. That, of course, is the left-hand side of the number. So over here is where I'm going to start counting. But I'm going to start with the first non-zero digit as the rule states. So I don't actually count that. Don't count. Don't count. So I'm still counting from the left with the first non-zero digit, and there it is. It's a 2. It doesn't matter that it's a 2, but there's your first one. So there's 1. And then you just keep counting until the end. So here's 1, and there's my second one. So there are 2 significant figures there. The second rule, please ignore that it doesn't have a decimal right now. We'll come back to that. But just know that any digit that's a 1 up to a 9 is automatically significant. Of course, this is skipping zeros, so zeros don't count. So start counting from the left. Any digit 1 through 9 counts. So yeah, all of those count. So that means that that number has 4 significant digits. Now, in the third rule, is where it's going to start to get hairy. Some zeros do count, like as opposed to up here when we said that skip all these first zeros. Down here, some zeros do count. Here we go. So it says zeros between non-zero digits are significant. So you see, if you look at these zeros are different than those zeros because these zeros are in between a 3 and a 5. So that means that all of those zeros count. So we'll still start counting from the left with the first non-zero digit. In this case, it's the 3. It's the very first digit. And we count all those zeros because they're in between a 3 and a 5, which are called non-zero digits. And then we, of course, count the 5 because it's digit 1 through 9. So that means that if you start here, it's 1, 2, 3, 4, and 5. That is 5 significant digits in that number. So we're going to split off a little bit from the general rules right now, and we're just going to do a second set of rules. It's called numbers with decimals. So here's the deal. So numbers without decimals. So numbers without decimals. If you have a 0 at the end of the number, it's not significant. So check this number out. It says 3,500, and there's no decimal here. It's like, where is that? It's not there. So there's no decimal. And that means that we do not count those two zeros. They don't count. So when I do the significant digit counting for this value, it's going to be 1, 2, but those other two zeros don't count because there's no decimal there. So there's only 2. Now for numbers without decimals, all zeros following a numbers with decimals, all zeros following a non-zero digit are significant. So that means that 0 will count because it's after a decimal. So this is everything I know about this number. So we start from the left with the first non-zero digit. So skip, that one counts, that 7 counts. And then this 0 actually counts as well because it's following a decimal. So skip, count. So this one has 2 significant digits. I'm going to go back and I'm going to do something called an overbar over all the digits that in that number that I consider significant. So in this first one, it's going to be the 2 and the 5. I'll try that again. And then for the next one, it's all the digits. For the third one, it is, so the 3 definitely counts and the 5 definitely counts, and the zeros in between also have to count because the 3 and the 5 count. For this number, it's only the 3 and the 5 because the 2 zeros don't count if there's no decimal. And for this one, it's the 7 and the 0. The 7 obviously counts because it always does, and then this 0 will count because it follows the 7, and there's a decimal there. So there is maybe a shortcut to some of this. So the shortcut is called the Atlantic-Pacific rule. It would definitely take the place of anything that you saw on the previous slide, but it doesn't have a lot of logic to it. It's just sort of like a trick. I don't know which one you would prefer to use, but I can tell you that the slide that we just finished is quote-unquote the right way to do it because it's traditional. So here's what we're basically going to do. With the Atlantic-Pacific rule, you just sort of throw out everything that you just saw on the previous slide, and you kind of boil it down to just look at the number. You think about the Atlantic Ocean and the Pacific Ocean. Just the Pacific Ocean is over here. The Atlantic Ocean is over here. So basically, when I say Pacific, I'm talking about the left. And when I say Atlantic, I'm talking about the right. So that's sort of the trick there. And the P in Pacific also stands for present, and the A in Atlantic stands for absent. And what we're talking about in terms of presence and absence is the decimal. So, for instance, right here, this number, we have a decimal point which is present. The P is going to clue you into it's the Pacific. and the Pacific is, of course, on the left-hand side of the U.S. So basically, when I look at this number, present, so go over to the Pacific, and you start counting with the first non-zero digit. That, of course, skips the 0 and starts at the 7. And then you just count until the end. 1, 2, 3. So that value has 3 significant digits, and I'll put an over bar just for clarity. If I take a look at a different example, like for instance, 1040. 1040 down here, the decimal point is absent. And that's going to give you a clue because the absent starts with the letter A, and so does the ocean, the Atlantic Ocean. So we're going to start on the Atlantic side since the decimal point is present. And you do something really similar to what we just did, only you start from the right-hand side or the Atlantic side. You basically just start moving in to count the digits, but you skip any zeros and you start with the first non-zero. That's a 4. So 1, 2, 3. That means that we have 3 significant digits in that value. There we go. Got it. All right. So we will do this pair up when I see you guys in class tomorrow. So you should write down these values or write down these questions in your Cornell notes for tonight, and we'll do them in class tomorrow. So please do have them ready. I will need you to do them as soon as we get to class. In summary, explain why 2.07 milliliters is a different measurement from 2.070 milliliters. I want you to answer this summary question in your Cornell notes tonight, and we will go over it in class tomorrow.